Okay, so we're going to look at analyzing our processes that we need to use when we are solving periodic motion or vibrational motion. So the first thing we want to do is we want to sketch a picture. Label what we know, label what we don't know. We want to visualize what is happening. We want to choose an object or objects. We may have to look at more than one system, it just kind of depends. So we are going to simplify what we can and we are going to diagram it out. We are going to figure out what are we assuming, what are we not assuming. And so we are going to need to take that into account. Now, the other thing that we're going to need to do is we are going to need to represent the process with force diagrams. We may have to do those. We may have to do bar charts for energy. So we're going to need to look at the system and decide what is it that I need to find, what would be the most useful information for me to have. So then we're going to move into the equations, kinematics if we need to, forces if we need to, free body diagrams might be useful, work energy bar charts. So we are going to use everything that we have done thus far this year in order to go ahead and figure out what it is that we need to look at. The last thing we're going to do is we are going to then solve. So there is a lot of work involved from the time you get the problem before you even start the solving. But the last step we've got to do is it reasonable? Does it look right? Because if it just doesn't look right, chances are it's just flat not. So, let's say that you are going down a ski slope and you are wearing a Velcro ski vest and you continue skiing on a horizontal surface at the bottom of the hill, running into a padded Velcro covered cart on skis. So go ahead and finish reading this question and we are going to start looking at what we're going to be looking at in order to solve this. So this is our example problem. Okay, so what is happening? I am going to be coming down some hill, right? At the bottom of that hill is a cart on skis. Yay. And here's my nice little person. They're on skis. They are going to be coming in, hitting this cart. That a cart is attached to the wall. It has a spring. So this is my wall. Okay, so what do I need to know? I need to know that the spring has a spring constant of 1280 newtons per meter. I need that the mass of the cart, this is going to be 20 kilograms. My person, or me, I have a mass of 60 kilograms. And that my speed just before I hit the cart, so my speed just before I hit the cart is going to be 16 meters per second. So the first thing I really have is I have a collision, right? So first things first, we have a collision. Now we're covered in Velcro, so we stick to the cart. So we have a completely inelastic collision. So we are completely So what that tells me is that energy is not going to be conserved, but momentum will be. So that is going to be my first things first. Momentum is conserved. So my initial momentum is going to equal my final momentum. Initially, I have a mass times velocity of me plus the mass of the cart, velocity of the cart. Finally, I have the mass of the person cart system, because we're sticking, times the final velocity. So I have 60 times 16. Now this velocity is 0, the cart's at rest, so this is going to equal 60 plus 20 times my final velocity. So that's kind of what I'm dealing with first. So as I work through this mathematically, I have 60 times 16. I'm going to divide that by 80, because that's what 60 plus 20 is. So 60 times 16 over 80. So that's going to tell me that my final velocity is 12 meters per second when I run that through my random number generator. So that was part A. That is my final velocity after the collision. That is reasonable if we say positive is down the hill going over towards the left. Sign matches because we're not suddenly going up the hill backwards. So then next we want to know is what is the maximum compression of the spring. So the thing is that we said that velocity max was going to equal the amplitude times the square root of k over m. So if I'm looking for the amplitude, which I am, maximum compression, I'm going to flip this over. So this is going to be velocity max times the square root of m over k is going to equal my maximum amplitude. So this is going to be the mass of u in the cart, so that's going to be 80. My spring constant was 1280. We just said our maximum velocity is 12, so I'm going to put all of this into my random number generator, and so I'm going to get my amplitude is approximately 3 meters. Now, the compression seems a little high. I mean, 3 meters, that's just right at 10 feet. So the question becomes, is that reasonable? Well, the skier was moving faster than 30 miles an hour. 10 feet of compression seems kind of reasonable for that. So the next thing we're going to try and find is the period of this amplitude, because that spring is going to push us back, right? So the period of our vibrational motion, so this was part A, this was part B. So period of our vibrational motion, I'm just going to work it here. So we are looking at the period being equal to 2 pi square roots of m over k. So that's going to be 2 pi. It's a system, so this is going to be 80 because we're still connected. Spring constant is 1280. So I'm going to plug all of that in, and I find that my oscillatory behavior is 1.6 seconds. So every 1.6 seconds, it's going to come into that 3 meters, or approximately 10 feet. It's going to go all the way back out and all the way back in. So our final question is, what is the maximum acceleration? So the maximum acceleration is going to occur at maximum amplitude. That's where our maximum acceleration is going to occur. It's when it's at its maximum amplitude, because we are pulling it back into the equilibrium the hardest at that location. So what we're going to get is that, if you remember right, the acceleration equation is negative amplitude times 2 pi over the period quantity squared times cosine 2 pi over the period times time. So that was our equation. So our maximum amplitude is going to occur when this cosine function is 1, which means we are looking at this right here for our maximum amplitude. Well, magnitude of that. So our amplitude itself, we're going to be looking at this. So if I look at my magnitude, so I've got my amplitude, so that's going to be here. I'm going to have 4 pi squared. Now my period, we have this equation for period, so I'm going to divide this by period squared, so that's going to be 2 pi square root of m over k quantity squared. So doing some math here, that's going to be acceleration, or the amplitude, times 4 pi squared over 4 pi squared. Square root of m over k squared is going to be just m over k. I've got a fraction divided by a fraction, so I'm going to flip that and multiply. And that's going to give me that my maximum acceleration is going to be the amplitude times k over m. So that's going to be that 3 meters. My spring constant is 1280. My mass is 80 because we're talking the whole system. So that's going to give me a maximum acceleration of 48 meters per second squared, and that's going to occur at the maximum amplitude. So thus far we have pretty much ignored the effect of friction. So without friction and without this idea of eventually there being a dissipating force, we would have our cars still bouncing from those speed bumps. Any bump in the road, our cars would just keep bouncing. We'd be going down the road, bouncing up and down everywhere. Our tall buildings would still sway after winds died down. So what we have is we have something that's called damped oscillatory motion. And what that means is over time, there is an external force that is going to reduce the amplitude of those oscillations until such a time they approximately go to 0 and they slow down to stop. So this is an example of damped oscillators. Basically, we have a mass on a spring and we can put it inside different materials, and what we find is that air slows down very gradually over time. If we put it in water, it slows down significantly faster. If we look at honey versus oil, you can see that it is coming to a stop fairly quickly. So the phenomenon of these decreasing vibrational amplitudes, it's called damping. And it's what we use in the design of vehicles, the design of bridges. So, I mean, if you think about it, let's go back a slide here. So here we have oscillatory. Here we just slow down to a stop, right? We don't even oscillate. It just goes towards a stop. So we use this damping motion, the idea that we can oscillate and eventually stop, in our cars, in our bridges. If we were out in California, or if we start changing some of our design codes because of our earthquakes, you're going to see that there is some damping motion put in place in building structures. So all real vibrations are damped. They will eventually stop unless there is more energy added to the system. If you do not believe me, go out on a playground, get on a swing, start swinging, and then just stop pumping your legs and see, eventually you're going to start slowing down. You're not going to go as high, and eventually you're going to come to that equilibrium position, that rest point at the bottom of a swing. So we are going to be looking at how these external interactions of the environment lead to this situation. So here we have a child on a swing. We are moving that out. So we apply an external force that allows us to initially drive that oscillatory motion. Without that external force, that's a driving force, we would not have that oscillatory behavior. So what you notice is that they are slowing down by applying a force to slow that backward motion of the child. That's an external force that is going to be slowing that vibration down. So what happens if you push at a slightly different frequency than what you're moving at? What you find is that there are times where you are adding to that vibration. There's times where you're canceling some of that vibration out. So even though you are doing positive work sometimes, there are other times you're doing negative work. And so your friction and air resistance are going to cause that swinging amplitude to decrease over time. Okay, so if you want to go through and read what I just talked you through, right here is that first experiment. The second experiment is here, where we exerted the push on the child. And then here we briefly pushed back as they swung towards. That's stopping some of that amplitude from happening. And here is the random pushing as well. So for an external force, the external force has to be a variable force if we are going to cause the amplitude to increase. It has to do positive work on that vibrational system. Now, here's the thing. In order to truly add into and to cause the amplitude to increase, the period, which means therefore the frequency of that external force, has to match the period of that vibrational system. So that leads us to a concept called resonance. Now, resonance is going to occur when some objects in the environment exert a force on it. It varies over time. So it's going to increase the total energy of the system and therefore the amplitude of the vibration. So the increase in the energy is going to occur when the frequency is the same. There is a video I am going to link of the Tacoma Narrows Bridge. This is probably our best and biggest example. It's also known as Galloping Gertie. So we are going to transfer an energy from one object to another. So that transfer depends on a couple conditions. The natural frequencies have to be close. And there has to be a mechanism that allows one object to do work on the other. So this is that Tacoma Narrows Bridge. This is a couple of screenshots from that video. Now, what you might notice here is there is a twisting of that bridge. So I'm going to challenge you to watch that video a couple of times. This is entirely done by wind blowing through the system, just through that channel. So watch that video. That's an example of a driving force. And the wind is the driving force that's adding the resonance to the system. And as you can tell, there is some catastrophic failure that happens. It collapsed in just 4 months after it was finished. So here are some of our summaries, and we've got a lot of equations this time. So we are having a restoring force with Hooke's law. We are talking a mass on a spring. Our period, which is 1 over the frequency, is equal to 2 pi square roots of m over k. If we are looking at a pendulum, our restoring force is connected to gravity and the length of that string. And so our period is going to be 2 pi square roots of L over G. That is for our simple situation. So we can go on and look at resonance and vibrational frequency, but at this time I'm going to challenge you to go ahead and work on your mastering physics.